Actually, it's recording now.
Yes,
recording
the
now.
recording is started.
So can you see my screen now? That's gone.
No, not yet.
We can't see.
That's exactly the problem. Just give me a moment. Like the recording has started. So share. Okay. Share screen. Start broadcast.
Yes, now you can see your screen.
Yeah. Now can you confirm it's like getting recorded as well
Yes.
as what is the record button here? Like not this red one, I guess. So it's this orange color one right here, right?
Oh, yes.
This one.
Mm.
Okay. So, okay, guys. So as Dr. Prabha said, my name is Chandrasekhar, and I'm at the Center for Quantum Information at IIT Madras as a scientist. So today I will be talking with you or teaching you about Schmidt decomposition. So let's start with seeing what the theorem, Schmidt decomposition theorem is. So we have a pure state psi AB. By psi AB, we mean this is a bipartite state. Okay, and it or not, it is in space. HA tends, so here HA is the Hilbert space corresponding to particle A and HB for B. And if we have a set of what do you call as orthonormal basis for HA and another set of orthonormal basis for HB, then you can write psi AB in this form, like some coefficient times, let me say this, I runs from 1 to k, some and E I for A, and sorry, not E, I mean here is F J for that is, you can write your bipartite state in terms of the orthonormal basis of A and B with some coefficient. Okay, with some coefficient here. And these coefficients, lambdas, are non-negative real numbers. Real numbers, and they satisfy this relation, lambda I square equal to 1. So this is theorem. So now if you want to prove this, it's like in terms of the basis vectors, we just have to write the set, let's say that H this and HB will contain, I mean, then your bipartite state, you can write this bipartite state sum for the first vector and for the second. And you will have coefficient C jk to look at the origin of where this Schmidt decomposition comes from, we
Excuse
should
me, sir.
go a little into, yeah.
So what do you mean by this notation that HA is contained in this set of basis vectors?
Okay, sorry. What I'm trying to say is, it is that thing. J's are the orthonormal or one of orthonormal basis for HA. And similarly, K is a set of orthonormal basis in HP. That's it. Okay.
Yes.
Yeah. Okay. That was a lousy notation. So let me get back to this thing. So we should see where the whole thing originates from. In a linear algebra sense, you guys know about what the Eigen decomposition of a matrix is, right? So if you are given a matrix, given a square matrix A, then you can square matrix and like B and QI be the eigenvectors. Okay. So you can always, if the matrix is, what do you say, like diagonalizable, then you can write this as A is equal to Q lambda Q. Okay. So this is the eigen decomposition of a matrix. So what we have done is write the matrix A in terms of a matrix Q, which is nothing but a n cross n square matrix with eigenvectors as the columns, and matrix lambda, which is the diagonal matrix with the diagonal elements being the eigenvalues. So if A is a general n cross n matrix which is divisible, so it should be diagonal. Okay. Then have the matrix Q, which is obtained by writing eigen. Okay, and then you'll have the lambda matrix, which is the diagonal matrix being the eigenvalues. So the actual advantage with this whole procedure is you can write arbitrary matrix in terms of the eigenvalues, and I mean you can represent it in a way that using just eigenvalues and eigenvectors. In matrices, eigenvalues and eigenvectors are some fundamental properties, like these are eigenvalues are invariant values and eigenvectors are invariant vectors of the matrix. Okay. So this whole thing works only for a square matrix, eigen decomposition. So our natural question would be like, what happens if we do not have a square matrix? What happens if it's not a square matrix? Okay, then we have a different procedure called singular value decomposition. We have a different It's actually similar to decomposition, but we have a generalization finally. Okay, composition of the matrix. So in short, we can call it as SVD. It is a factorization of a real or a complex matrix, which is m by n. So if we have a m by n matrix, we can factorize singular value decomposition. Okay, so you can write a singular value decomposition of a m matrix m, or matrix m in the following form: U, then another matrix sigma, and another matrix V. Okay, so here I'd like to mention that the sigma I'm using here, it is a matrix, not the symbol for summation. Okay, so here capital M is a m n matrix. Sigma, no, not sigma. Let's look at what U is. Okay. U is a m unitary. Sigma is a m cross n matrix. And V cross n complex unitary. Both m and n are complex unitaries. So, okay, so unitary. So now to explain this, let's say my matrix here is like this: 1, 2, 2, 3. Okay, so you can see this has 1, 2, 3, 4, 5. 1, 2, 2, 3. Let's consider this is the M matrix. Okay. Then we can write this in terms of 5 by 5, and then again 5 by 4. That will be okay. So 1, 2, 3, 4. Now the diagonal things would be along here. So you can see this is, you will have 4 diagonal elements. Though it's a 5 by 4 matrix, it will be a 4 diagonal element. 4 diagonal elements. Okay. So the diagonal values which occur in the sigma matrix, the diagonal entries of the sigma matrix let's say sigma is this, then the diagonal entries are the sigma ii. Okay, these entries are the singular values of matrix M. So the number of non-zero singular values is called the rank of the matrix. Okay, if we have a matrix M, the rank of the matrix is the number of the non-zero singular values. Okay. So the singular value decomposition is not unique. So we can choose any decomposition. In general, what we do is we choose a decomposition where the singular values are in the descending order, like the highest value first, and then it keeps decreasing, like 5, 4, 3, 2, 1, and let's say the rest of 0. Okay. So next we will try to prove this singular value decomposition. Let us consider a M cross M complex matrix C. Okay, C is a M cross M complex matrix. And we can decompose C as follows: U, D, V. U is the M cross M unitary. V is the M cross M unitary. D, the M cross M rectangular diagonal matrix. So if you want to know how many entries will be there in the rectangular diagonal matrix, you should look at the index M and M and find the minimum of this index M, M, and then the number of entries R will be less than or equal to this minimum entry M. Yeah, Mn. Because if you write the diagonal, as you can see here, this is a 5 cross 4 matrix. So if you start from 1, 1, 2, 2, there is 4, 4, and beyond that, I think you don't have anything. Okay, so between the rows and column, you will have to choose the one which has the lowest number, and you will have you can have as many diagonal entries as this minimum number, but you can also have less because some of them can go be 0. Okay. So here R is the let's say number of non-zero entries on the diagonal. And this R also represents the rank of the matrix. Okay. So next, let's consider a matrix M. Which we write as C dagger C root of. That is, we have a C matrix which is M cross M. Okay. Now, if you take C dagger C, this is a M cross, and this will be N cross M, and this will automatically become N cross C. So, our matrix capital M is a N cross N square matrix constructed. Okay. Now, let us consider the unitary V and take V dagger M V. Okay. Here we know that V, we are considering V because the N by N, if you look at what we have written, this is the N by N unitary matrix. So we write V dagger M V, and this we can write as C dagger C times V, and that will be equal to some diagonal matrix. Okay. And again, this diagonal matrix will be N. Now, let D, the diagonal matrix, have non-zero entries. Then we can write V as a matrix with small r and pick up only the first r columns of V1. We can write this matrix V and pick up only the first r columns and write the new matrix V1. This new matrix would be a N cross matrix. Okay. The remaining part of the matrix, which we have not picked up, will be the N into N minus R cross matrix. So what we have done is we have split our matrix, unitary matrix, into two parts, V1 comma V2, where V1 is a N cross R matrix and V2 is a N cross N minus R matrix. Now, if we let this V1 and V2 act on this C1, I mean, like, actually we can similarly split the C matrix into C1 and C2. Then again we can split C equal to C1 comma C. Again C1 would be N cross R and C2 would be N. So if we split this, I have C1 dagger C. This will be D1 and V2 dagger zero. Okay. So now we can define, just earlier we defined C is equal to U dV, right? U dV. Now we can define U1, this new matrix, which is part of the U matrix as CV1 D1 inverse. So this will be a M cross R matrix. Now we have to check if this is unitary. So we can actually do U1 dagger U1 and write this. That will be like D1 inverse, V1 dagger, V dagger C, and V1 again D1 inverse. Now we can split the C dagger C in middle as follows. C dagger C D1 D1 inverse. Now the unit V1 to write. Now this whole thing is D1. Sorry, there's my minus, there's plus one. So this whole thing is D1. Okay. And again, this whole thing is also D1. So this is equal to unit matrix, and which means we verified that U dagger U is equal to identity. Okay. Now we have U1 is a M cross R matrix, and now we can add rows to U1 to make. Okay, let me write it down. U1 is a M cross R matrix, but we want a M cross M matrix. So we can add more rows to U1 to make it into a M cross M matrix such that U is equal to U1 comma U. Okay. Now U B V dagger is equal to U1 U2. Now we have the D1, which is the non-zero part of that, and the other part is 0. And V1 dagger, V2 dagger. So we have proved that C is equal to U D V dagger. Now C is a arbitrary matrix of size M cross M, and U is an arbitrary matrix of size M cross M, and D is M cross N, and V dagger is M cross N. So we have actually taken matrices of different dimensions and constructed a kind of a decomposition. Okay. Now, thing is the general matrix C, which is not diagonal, has been decomposed into a diagonal matrix where the diagonal entries are the single. So, do you guys have any question up to this point? Hello. I hope you don't have any questions after this. Now, we can note some properties of this here. if we have the matrix V, the columns of this matrix V are the vectors. So for U, the columns of U are of CC dagger. So you can see this using this. If you have C dagger C, you can write C and C dagger in this form. So this for C dagger, then this is, then you have V E E C, and then C C dagger, then U D V dagger, okay. So we have finished this Schmidt decomposition. Sorry, the proof of the singular value decomposition. So now if you will get back to Schmidt decomposition, the it's show like so. If you have a bipartite vector A B, as I wrote down already, you can write it as JK, J, A, K, B. So using the solution, we can write C, JK to B. So it exists only for P comma Q lies between 0 to R, and otherwise it is 0. So mathematically we can write as it between P comma Q R and 0 otherwise. So we can rewrite the state psi using the CJ summation as follows. Like you can write it as UJP So I can actually split this into two parts, two summations, dpq, and then there is another sum here which 1 to dA. So now we can define these two parts as some vectors, okay, the basis vectors. So E, E, A. We can see these two vectors, E and F, are the condition, that is EL PI is equal to and FL. Okay, so these are orthonormal bases, and so we can write the state psi AB as some kind of okay. But now we had this condition where we can use this condition dpq is equal to delta pq dpp. Okay, and we can write this as this. So you can see we can split the vector. We can write down the vector in in terms of the eigenvectors of the sector A and eigenvectors of the particle B with some coefficients, just like we had in the initial definition, like psi AB is equal to sum over I is equal to 1 to K lambda I Fi. Okay, so do you guys have any question up to this point? Hello. Dev Jyoti.
Yes.
Yeah. So actually, was I audible all the time? Like,
Yes, it's clear.
was the video and things good? You guys didn't have any problem.
No problem.
Okay. So, guys, have any questions? Anybody has a question? No. Okay. So let's move on to the applications of Schmidt decomposition. One of the usefulness of Schmidt decomposition is in calculating the, or not calculating, we should say like finding the entanglement in the system. So if we write a state in the Schmidt basis and if we write the reduced density matrix in the Schmidt basis, we have a, let's say psi AB is my state. Okay. And if I write it in the Schmidt basis, and carry reduced density matrix. We will find that row A and row B have identical eigenvalues. Okay, so here we have to define what do you call as something called a Schmidt number or Schmidt rank. So let's say you have a state psi A B. The state psi A B in the Schmidt basis, and once you have written the Schmidt basis, you will have to count the number of non-zero Schmidt coefficients. Coefficients are okay. We'll have to count the number of Schmidt coefficients, and that is called the Schmidt rank of a system. Schmidt rank of the system. So, and this Schmidt coefficient is a measure of how entangled the system is, and it can run from 1 to number. So to give what this number is, if you have a bipartite system A and B, okay, let's say A has dimensions dA and B has dimensions dB, because you're not always going to look at qubits or qubits equally. Sometimes you might look at a qubit entangled with a qubit kind of a situation. So if you have dA and dB be the dimensions of A and B, then system A and HA is the inverse space zone. Okay, and HA has dimensions dA and HB is the dimension for dB. Okay, so you find the minimum dimension of this dA and dB, and R runs from 1 to this. Okay, for example, if you have a 2-qubit system, your dA is equal to 2, your dB is equal to 2. So your R will run from 1 to 2. Okay, so if you had dA equal to 2 and dB equal to 3, this will again run from 1 to 2. So if the Schmidt rank is 1, then the system is entangled. But if the Schmidt rank is greater than 1, the system. Okay, so what happens if the Schmidt rank is equal to 1? If it is equal to 1, you can always write psi AB equal to E1A tensor F1B. That is as the product state. Okay. So that's one of the advantages of Schmidt decomposition. Then you can see if we have let's say for this entanglement entropy. Let's say you have a state psi AB, and this will be equal. Okay, so let's say we have a bipartite state, and rho A and rho B are the reduced density matrices, and lambda I squares are the probability distributions. So the entropy for this is lambda I, which over I lambda I square log I square, and so we will have a situation where the reduced density entropy reduced density matrix will lie between between 0 and the Schmidt rank of the system. Okay. So if the state is a product state, then we have lambda I square is equal to 1, and consequently we have this equal to 0. So the entropy of the system is 0, which means the state is not entangled. So if the state is maximally entangled state, then we have R will be at the maximum value, which is the minimum of dA and dB. Let's say if it's a qubit system, then dA is equal to 2. So we will have lambda square is equal to 1 by 2 comma 1 by 2. That will actually give us to substitute in the entropy form. This will be minus log to the B2 times to log 2 for each eigenvalue. That will be like log 2 to the. But if we have this for arbitrary dimensions, let's say we have d equal to small d, and you will have 1 by d of them, then you will have 1 by d times log. And so on. You will have this expression 1 by d times. So, okay, there's a minus overall outside. So you do this, then this log, d times. So this d will cancel with this d. This will be log d. Okay. So for a maximally entangled state, the entropy would be like log d to the base 2. Okay. Okay. So do you guys have any questions? Hello? So Deb, hello, Debjyoti?
Yes, yes, yes. Mm,
So
mm.
I think I have already taken more than 5 minutes of the class, right?
Oh, yes, it's 10:57.
They may have other classes, right? So
Mm-hmm.
yeah, okay. So one quick thing, Deb, can you check if the class is being recorded? Is like,
Yes, it
do you
says
have
the
any idea?
meeting recording is in progress. That's, I think it's recorded.
Okay. Okay. So, okay, guys. So, do you guys have any questions up to this point? Yeah. Okay. So, if you don't have any questions, so we'll call it off. And yeah, I think Professor Prabha will continue with the rest of the things from the next class. Okay. Okay. So, I think we can stop
Excuse me,
the
sir.
recording. Yeah, please.
Sir, will you be sharing your notes with us? Thing that you just wrote.
You mean this handwritten
Handout.
thing, right?
Yeah.
Oh, sure.
Thank you.
How do I do that? How do I do that? Like,
Yes,
Uh,
send it to me. I will share with them.
okay, then.
The notes and the recording also.
Recording. Where does this gets recorded? On the cloud or in my
I think
my
it's in
device?
the cloud or in the WebEx app. I think so.
Okay. Do you have any idea of how do I get to send it? Like, I'm new to this whole thing, Dave. Like, can you help me with this?
Oh, I think okay, I will share a link to you. You can see from that.
Okay.
Uh-huh.
Okay. Okay, then. So I think I will stop the recording now.